Example 1 asks us to expand each of the following. We have the quantity 2p plus q cubed, and we have the quantity x minus 3 to the fourth. Well, each of these are just binomial expansions. So you could take each term, multiply it all the way out, or you could use a little kind of analytics in order to make things a little bit easier on yourself. Well, we learned from the intro activity, there's the thing called Pascal's triangle, which says that if we had a binomial a plus b to the n, if n was 0, we would just be left with the number 1. But as we increase values of n, our coefficients of the terms that we have left begin to make a pattern where we always have 1s on the ends, and the sum of our term, or excuse me, the sum of 2 consecutive terms makes the term below it. That's not 4, that's a 6. And so the way this works is that a gets all of the powers of n to start. Or excuse me, this next one. And then it trades them as they go down. So a is going to get all of the a's. It's going to be a to the n there, and then it trades and it goes down, and then so this one then gets a to the n, and so on. So that's how this is going to work. So let's look back at these problems. So for this part here, we start out, this is a cube, so we know that we're going to have, if we go back to our part here, we're going to have a 1, 3, 3, 1 pattern. So it's going to be 1, 3, 3, and 1. Okay, so what parts are going to be there? Well, you're going to have 1 times 2p cubed. And technically the q is going to get the remainder of the powers, which is 0. Then we have 3 times 2p squared, and now the q gets one of the parts. And then we have 3 times 2p to the first, and the q gets 2 of the exponents now. And then finally, we end up at the very end where we get plus 1 times 2p to the 0, so it's gone, and we get q cubed. So they trade off in that pattern. Now the 3's represent the number of different combinations of those terms, like when we get kind of like terms throughout an expansion. So we can go forward and actually solve this out. Here, if you multiply these terms out, you're going to get 8p cubed. And then this is going to be 3 times 2 squared, so it's going to be 12 p squared q. We're then going to have 3 times 2, so it's going to be 6 p q squared. And then finally, we're going to have plus q cubed. So that's the answer to our first part. Again, the 2 kind of makes things a little bit weirder, but at the end of the day, this is what you're going to end up with. Okay, so let's look at the second one. Second one is x minus 3 to the fourth power. Well, we go down to where the not the fourth row, but when n is 4. So you're going to have 5 terms, and you're going to have a pattern that looks like this. So we've got 1, we've got 4, we've got 6, we've got 4, we got 1. Okay, so we start off for the 1, x is going to get all of the exponents. So it gets 4, and then negative 3 gets 0 of them. And then 4, we get x gets cubed, and then negative 3 comes out once. And then we have x squared, and the negative 3 comes out twice. And then we have 4, just regular x to the first. The negative 3 gets cubed. And then finally we add x gets zeros, and negative 3 gets to the fourth. So now we've used our pattern to help figure out how it builds, and now we multiply to get the remainders, or to get, get the final answer. So right here, this is going to make x to the fourth. So now we have 4x cubed times negative 3, so this is going to be minus 12 x cubed. We then have 6 times the negative 3 squared, so 6 times 9, so that's positive 54 x squared. We then have negative 20, we have 4x times negative 27, so that's going to be negative 108x. And then lastly, we have x to the 0, which is 1, times negative 3 to the fourth, which is 81. So it can actually be a lot easier if we have to do a huge expansion to think using the Pascal's triangle, instead of having to keep going through and multiplying term by term by term by term by term, we can understand the pattern and follow it from there.